and its overhead electrification. Can the negatives outweigh the positives? A couple of notes on Ricardo, who very kindly let me have a bit of the afternoon to do this presentation. Right, so why a Google Earth view of a castle? I'm not asking you to identify the castle, that'll become clearer later on, but it is germane to this talk. So, as we just said, electrification, particularly overhead electrification at high voltage, is generally seen in a positive way. Typical benefits claimed include the simplification and reduction of cost of rail vehicles, local elimination of pollution, especially if the alternative is a diesel-powered vehicle, and a cleaner image. However, there are wider cost and external effects. These are not always fully thought through as an electrification scheme moves from the feasibility stage through design and construction to taking into use and to the operations and maintenance phase. Starting with implementation issues. Typically, physical implementation requires significant disruption to train services over months, if not years. This can destroy the rail market on the route and thus, potentially, electrification's own business case. For example, electrification of one commuter route required the suspension of evening and weekend services, forcing passengers to use alternative modes of transport. As the electrification works coincided with the recession, those other modes were not crowded, and there was a degree of modal shift away from the railway that took a long time to recover. Although it is now the practice to install signalling assets that are designed to be compatible with future 25 kV overhead electrification, this was not necessarily the case in the past. Therefore, where electrification does not coincide with resignaling, there can be a significant amount of work for the immunization of the existing signalling, including, in particular, changes to track circuits. The design life of a bridge is typically of the order of 100 to 120 years. Some forms of bridge, such as brick and masonry arches, can, if the foundations are not disturbed, last much longer. When electrification requires the reconstruction of bridges, it has to be recognized that there is a cost in environmental terms of destroying bridges with decades of remaining life. There does seem to be some potential for a former practice. The London, Brighton and South Coast Railway electrified much of its suburban service in the early years of the 20th century, using a 6.7 kilovolt AC overhead system. To avoid reconstructing certain bridges, there were dead lengths of contact wire. This concept is now being promoted as an innovation, although recent experience is still limited. The trains could deal with quite a long dead section. Up to 60 metres is recorded in Hamilton Ellis's The London, Brighton and South Coast Railway. Great Western electrification introduced the concept of combining surge arresters and insulated coatings at the Cardiff intersection bridges, avoiding difficult reconstructions. It will be interesting to see how the coatings perform over the years and how often they have to be refreshed. In that context, there is also a need to ensure that the insulating coating or an equivalent remains on the market. Incidentally, this is now a standard network rail solution and has been used recently on a lot of structures on the Midland Main Line. So this is some images of the GLS coating and the NR accepted surge arrestor. It's taken from material supplied to the Ricardo certification. We were the assessment body. In fact, I was the assessor in support of network rail safety justification. One alternative to bridge reconstruction is track lowering, where, as is often the case with older bridges, the abutment design relies on the presence of passive earth pressure on the lower face of the abutment for stability. The abutment needs to be underpinned. Unfortunately, there is usually also a need to modify the drainage to avoid the creation of a sump. Track lowering adversely affects the track top profile. On a higher speed line, there is a need for long run-ins and run-outs to comply with the relevant design parameters and to avoid the creation of a permanent speed restriction. This work inevitably requires possessions longer than the maintenance white periods and, not infrequently, temporary speed restrictions whilst the new track profile is created. As with bridges, there is a cost in environmental terms of changing an existing asset configuration with remaining life, generating ballast and track waste. A second alternative to bridge reconstruction is the installation of a track slab, common where there is a tunnel or a succession of bridges. It is rare that construction of slab track does not require a blockade of the track for a period more likely to be measured in weeks rather than days. In addition, the construction of transitions between track slabs and ballasted track can be problematic in terms of quality control. Electrification also requires a significant earthing and bonding exercise. It is necessary to consider all existing metal structures, including footbridges, line-side fences, station furniture, etc. At metal bridges, the risk of dangerous touch potentials must be eliminated. So moving on to the increased need for on-site work. Whilst rolling stock can be maintained offline in warm, covered accommodation, protected from the weather, with plant, tools, support, etc. to hand, electrification assets have to be maintained at height, often at night and in the pouring rain, and in winter in the freezing cold. This makes achieving quality difficult and introduces additional safety risks, and if problems arise, support is remote. Although train-mounted remote inspection techniques are now quite sophisticated, there remains a need for some physical inspection. The same issues arise as for maintenance. The need to use access platforms, whether train or plant-based, means that there is a need for track access and, of course, for isolations of the electrification system. Difficulties for other assets. Where the presence of electrification now means that track access for work also requires an electrical isolation, there is a significant reduction in available work time. It is not the isolation itself that takes the time. This is merely a matter of switching. It is the need to secure against re-energization and to apply earths. There is a common misconception that the requirement to apply earths during an isolation is to deal with the possible presence of induced voltages due to adjacent live electrical equipment. While it is true that such voltages do occur and are sometimes remarkably high in the thousands of volts, this is not the primary reason for the application of earths. The primary function of the earths is to provide the security of the isolation from inadvertent re-energization as required by Regulation 13 of the Electricity at Work Regulations, SI 1989-635. Until the earths are applied, the overhead electrification equipment can only be said to have been switched off in compliance with Regulation 12. And it's worth noting that the requirements of both Regulation 12 and Regulation 13 are absolute. The use of risk assessment to support an as low as reasonably practicable argument is not permitted. Unless the switched off equipment is secured against inadvertent re-energization, it cannot be said to be isolated, and it would not be appropriate to issue any permit to work. It should be noted that the regulations have not been made as a result of European safety legislation, and that there are different electrical safety requirements in different European countries. Permanent earths have been tried. They were used on the original British West Coast Main Line electrification in the 1960s. However, many earths were used very rarely and became unreliable due to dirt and corrosion, etc. It was found that a significant ongoing effort was required to ensure that they were 100% effective. Hence the current normal practice of designated points to facilitate earth attachments, although quite a lot of work is going ahead at present to try to demonstrate that alternatives to the original permanent earths are successful. I've had practical experience of these issues. As a maintenance manager in the Birmingham area, I could contrast work on the electrified Rugby Birmingham Stafford lines with the non-electrified Derby Birmingham Bristol lines. During my work as implementation strategist for West Scope's route modernisation, I started to review the post-modernisation inspection and maintenance workload for each asset and assess whether the track access was sufficient. It was a factor in my work for High Speed 1 Control Period 2 track access charge submission. I had to explain to the regulatory hearing the relationship of cost, available work time and quality for the inspection and maintenance work. Hours of operation are much longer than on the French ligne à grande vitesse, as the Javelin service starts early and finishes late, and there may be some limited freight traffic, although I understand there's none at the moment. And unlike France, there is no daytime white period. This is a worked and far from extreme example. We're assuming the white period, the no trains period, is 4 hours. So you're applying the earths, half an hour, could well be longer. You then have to mobilise on site, half an hour. You get 2 hours work, and then you have to go through the process again, making sure everybody's off, surrendering the permit, that half an hour I've said, and remove earths half an hour. And longer sites require earths at least every 400 metres. Second work example, without isolations. Mobilise on site as before, half an hour, and clear site half an hour, but now you've got 3 hours for work. So in a 4-hour white period, you've increased your effectively time by 50%. It's also an issue, but perhaps less so, for conductor rail electrification. The electricity at work regulations lent to much greater use of short circuiting straps, but these are easier to attach than OLE earths. In addition, many OLE routes are mixed traffic and without electrified diversion routes. Conductor rail track is often on commuter routes or multi-track main lines, many with electrified diversions. Extensions to white periods are therefore easier to agree. As noted earlier, the overhead electrification asset requires track access for inspection and maintenance activities. This means that for those wishing to carry out maintenance and inspection work on other assets, including track, signalling and structures, there is an increase in competition for track access to carry out that work. Where a line is electrified on the overhead system, track must be maintained to tighter tolerances. This is particularly important for cross-level, as the effects at track level are typically multiplied 3 times at contact wire level. Care must also be taken over the maintenance of top to avoid affecting contact wire gradients and of alignment. On straight track, the contact wire is arranged in a zigzag pattern to minimise the risk of wearing a groove in the pantograph contact strip. On curves, the contact wire takes the form of a series of straights. In both situations, the track alignment must be managed to ensure that the pantograph remains in contact with the contact wire. This need to maintain to higher tolerances means that track access for maintenance is required more frequently than would otherwise have been the case. However, if you're talking about a high-speed line, the need there for precise management of track, cross level, top and alignment usually means that the presence of overhead electrification is less of an issue for this particular point. As the rails are used as the initial return for the traction current, great care must be taken when carrying out work not to interfere with the path. The red bonds, which are part of the link between the rails and the return conductors, can, in some fault conditions, be live at 25,000 volts. Extension of electrification increases the presence of bonds. This is in contrast to signalling, where the increasing use of axle counters reduces the number of bonds attached to the rails. The need to maintain 3.5 metre clearances to live overhead line electrification equipment, and we're not just talking about the contact wire, complicates the maintenance and cleaning of station structures, particularly platform canopies. Where the introduction of overhead electrifications meant the installation of sections of slab track, for example through tunnels or under a succession of bridges, there is a need for transitions between the track slabs and the ballasted track at each end. Because of the varying degree of rigid support, the transition is difficult to maintain, with additional attention and thus requirement for track access having to be paid to cross-level and top. There is a need for additional vegetation management, particularly where there is a risk of tree branch contact with unsheathed return conductors, requiring further additional track access and isolations. And this was one of the big problems on the Rugby Birmingham Wolverhampton Stafford line. Vegetation in the deep cuttings was a major issue, keeping it away from the return conductor. It's a single point of failure. Overhead electrification introduces a new failure mechanism for the railway, in that a loss of power immobilises the train, whatever the state of the non-electrification engineering assets. Accordingly, many suggestions for mitigating electrification failure consider how power can be brought to the train. However, a failure of the mechanical electrification system is unlike the other engineering assets. There is essentially a single point of failure which cannot readily be mitigated to allow trains to pass and clear the line. Concern about this type of failure with a transmitted power system goes back to the earliest days of railways and the debate amongst the proposers of the Liverpool and Manchester Railway about whether cable haulage or locomotive haulage was the way forward. And similar discussions of principle surrounded the atmospheric system. In many situations, a failure of the catenary system or a headspan means that the clearance required to pass trains is infringed. This affects non-electrically powered trains as much as electrically powered trains, although the non-electrically powered do have hotel power whilst waiting for the situation to be resolved. Objects blown onto the railway obviously cause the suspension of train services whilst they are removed. However, where the line is electrified, there is an additional likelihood that, for example, plastic sheets will be caught, and then an additional problem in that the removal requires the electrification to be isolated and made safe before the object can be removed, increasing the time required significantly. I'll come back to this one. Manage degradation. In contrast, failures of other assets are often amenable to mitigation, which will allow the movement of self-propelled trains, so reducing the disruption to passengers and freight customers. If a broken rail is reported, then processes are in place, for example clamping, which will, in many situations, allow trains to be passed. This may possibly mean the train moving at walking pace and with inspection required after every movement over the brake, but at least movement is possible. Similarly, a developing track cross-level twist or a subsidence can be dealt with by packing the track between trains and, as necessary, allowing movements at walking pace. However, this may not be possible where there is overhead electrification because of the need to maintain the pantograph/contact wire interface within tolerance. When the track has buckled, it is possible, if space is available, to slew the track to form reverse curves that will allow movements at slow speed. However, this may not be possible where there is overhead electrification, again because of the need to maintain the pantograph and contact wire interface within tolerance. Where an underbridge has been struck by a road vehicle, processes are in place which can, subject to conditions, often allow a movement at walking pace pending structural examination. Points can fail for many reasons, but it is normally possible for them to be operating manually by staff on site in accordance with the signaller's directions to permit trains to pass. When the control system fails, various mitigation measures can be introduced, depending on the nature of the failure. Movements may be authorised through a section at caution, or station-to-station working may be introduced. If the failure is likely to remain for an extended period, ticket working may be practicable. If the signalling fails on a single line, pilot working is introduced, in which a clearly identified person effectively acts as a human staff. So, whilst the introduction of overhead electrification may have benefits for the operation of the system and for its users, it must never be forgotten that there are significant operational and asset management disbenefits. These must be carefully considered as part of the commercial analysis of electrification proposals. So, what are the environmental alternatives? Hydrogen engines can use modified diesel engines, but fuel tank capacity to meet heavy freight loco range requires tenders. You'll see that on the next slide. You can have hydrogen fuel cells, batteries, liquid air, and potentially liquefied natural gas as an interim. Not an alternative. Some of you may recognise the image on the left. It's what was called a brake tender. And it was used to increase the braking capacity when diesel locomotives were introduced and trains were moving at something higher speed than steam to help control partially or unbraked freight trains. And initial thought, when Ricardo carried out some work on hydrogen for freight in early 2021, was that the hydrogen would go into a vehicle about the size of a brake tender, which, as you can see, allows the driver visibility over the tender, so can see the signals and everything. However, hydrogen is not a high energy fuel. The initial thought, as I say, was something the size of a brake tender, but calculations showed that the tank wagon on the right, in the right photograph, was not actually enough for current ranges. Even though it's a huge tank wagon, it wouldn't allow a diesel engine to do anything like the same range as the current diesels do. The left-hand photo is Florida East Coast. The right-hand photo is a Russian loco. What they both have in common is liquefied natural gas as a fuel. And obviously they're a lot longer than normal locomotives. Florida East Coast has it straightforward. Although its trains come and go from the whole of the United States and potentially Canada and Mexico, Florida East Coast's locomotives only run on Florida East Coast, which is about 300 miles up the east coast of Florida. So it's fairly easy to arrange for refueling on their system to fill the little tank wagon that's between the two locomotives. The alternative becomes a problem at locations like Felixstowe. Felixstowe, as shown in the front photograph, has rakes of sidings used by the container trains. And to allow the locomotives to run round, it has a traverser rather than a long raft of S&C. And you can see it in the rear of the photograph. You can see the traverser there. Now, whether it's S&C and you need longer head shunts for the double locomotives, or whether it's a traverser, there would be an awful lot of work required to introduce hydrogen locomotives with tenders. There's also issues with the supply of hydrogen. Train operators in Germany are withdrawing hydrogen-powered trains due to difficulties in maintaining an adequate supply. That was in Modern Railways in February 2025. And bus operators in England have been refused permission for hydrogen storage as, for a fleet of 97 buses, the 5-ton facility required is a COMA, control of major accident hazard sites, and the HSE advised the council concerned against granting planning consent. So there's 97 buses on order, but no way of using them as hydrogen buses. And that came from the Chartered Institute of Logistics and Transports magazine last summer. That's a major problem to be sorted before there's a major rollout of hydrogen buses, because most coma sites where you want to stable buses are going to be close to things that HSE might be concerned about. There is a non-environmental alternative. After many years, the line from Preston to Blackpool was electrified, allowing for electric trains to run all the way from London. The trouble is that after it was electrified, Avanti will use it, or Virgin first and then Avanti continued to use the Voyager diesels. And there were two here that I was travelling on, and I was just so depressed by the fact that after all the electrification, people were running 226 miles in a diesel under the wire all the way. So, back to the castle. One of the prompts for this presentation was a incident on a journey from Bristol to London. I was in a HST. The electrification at that stage only extended as far as the junction for Heathrow Airport. And about 5 o'clock, we came to a stand at Slough. And the conductor opened the doors and he said, "Don't wander very far." But, obviously indication people could use it as a cigarette break. He said, "There's problems with the OLE on the way to Paddington. We expect to be here for about half an hour." At about 5:25, he came back onto the public address and said, "Unfortunately, there is a need to isolate the overhead wire to remove a plastic sheet. We will be expected to arrive in Paddington at about 8:30. However, South West Trains have agreed to pass, and at that point there was a mass exodus of the train, a stampede over the footbridge to the Bay platform. The 17:30 shuttle to Windsor and Eton Central left full and standing. And then along the pavement to the left of this picture, there was a stampede of people jog-trotting along the foot of Windsor Castle to Windsor and Eton Riverside. And I was thinking, as one of the people doing the jog-trot, I've been sat on a HST which has got no problem with it. There's no problem with the track, no problem with signalling, but there's a problem with the OLE. So there we go. So, thank you.
Thank you very much indeed, John. That was an excellent presentation. I thoroughly enjoyed that.
Right.
I'm going to move over to the questions. Colin, would you mind reading them out from the chat, please?
Yep, I can certainly do so if we had some questions in the chat.
Right.
So I think your presentation must have been very encompassing, because anyone who had any questions has obviously got some answers.
It was a bit rushed because I know you like to try to keep it to just the hour. So normally I'd be a bit slower on each slide. So give people a couple of minutes just to recover from the mad charge through. I've previously done it in longer sessions, but there we go. It's the same presentation. It's been updated a couple of times.
I think just on reflection.
I've got a question. Yeah, sorry, go on.
No, go on, Phil. You go ahead.
Go on, Phil.
Yeah, no, I've got a question which is probably a bit unfair, but I wondered whether you were aware of any developments with something I heard must be a year or two ago now, which was to do with the overhead line electrification of the Marsh link. Now, you know, the HS1,
Yes.
the OLE equipment extends from HS1 into Ashford platform.
Station. Yes.
Into the station and back on again. But over on the west side of the station, they were thinking about extending that OLE round towards Ham Street, you know, on the Marsh link towards Hastings. And I think they were talking about.
It's going to be a fun
Yeah.
PWI exercise to get from around the corner, isn't it?
Yeah, I think that what they were looking at is javelins from maybe Hastings if you can get through Ore Tunnel, but if not, short of that. But having a javelin service using high speed 1 coming up the Marsh link. Yeah, there was a bit of a lobbying exercise for that. I just wondered if you knew anything about that, or
no. I mean, I know there's been
yeah.
lobbying for it. Speaking as a permanent way engineer, as you know, and somebody who knows Ashford, my reaction was, how are they going to get a connection that allows you to come off the high-speed 1 lines, actually using a platform, and then get round the corner, because you've only got the one platform from memory, and it's the back
That's
platform.
Right, yeah.
You know, so it's as much a track problem as anything. But
yeah, I think there would need to be significant track works on the west side of the station.
And station works.
Yeah, and structural works as well,
Yeah.
you know,
I mean,
bridges over the, yeah.
What's tragic is that at the time the new diesels were introduced in the, or being thought about, was that I was working on West Coast route modernisation as the implementation strategist, and was looking at disruption costs, Schedule 4 disruption costs. And of course, on the West Coast, where you've got everybody and their dog running trains on it, the disruption costs were very, very high, particularly for TOCs that got very little benefit from the route modernisation. You know, obviously West Coast, you would be balancing it against their benefits, but the ones who just came on and off, delaying them and the commuter service and whatever, and the disruption costs were getting on for 30% of the costs of the work. And at the time, this was the only disruption cost that people had. And the DFTs were using them, I understand, as a benchmark for other major projects. But at the time, the Uckfield line sort of closed from Saturday night to Monday morning, and the Marth closed in the winter from Saturday night to Monday morning. And so the disruption costs for actually doing conductor rail electrification would have been very low. It's just a shame that you know, it was the early days of privatisation and nobody had a clear handle on it. It could have been electrified on conductor rail system then. There wouldn't be the issues there seems to be now with conductor rail. And it would have been quite easy with the, you know, the craned in, ready built substations and TP huts. It could have been done then as a, because remember the Javelins have got a third rail capability, so you know there would have been just the track work needed.
Yeah, no, that's a good point. Yeah.
I mean, the one that's still a double track tunnel down there is Mount Pleasant. I don't know what the clearance is like in Mount Pleasant.
Yeah, there's a comment in the chat about Ore Tunnel. Yeah, I am aware it's a single track, but I wouldn't know off the top of my head whether it's suitable for overhead line. But
it's the other one that you'd have to look at, the one from Ore to Hastings, the Mount Pleasant.
Yeah.
Well, it'd be fun having OLE along the line with semaphore signalling, wouldn't it?
Yeah, I think third rail will come at some stage on that line.
Yeah, it's. I think it's the obvious.
They'll have to. Yeah.
Are there any more questions for anyone? I'll take that as a no. In that case, I'll pass it over to Colin Bergnall, Vice Chair of the Ashford Section, to do the vote of thanks.
Thank you, Phil. So, John, thank you for stepping into the breach. I thought the presentation was insightful and thought-provoking in equal measure. Looking at the alternatives, hydrogen, diesel, and then reflecting upon the title of your presentation, overhead line electrification, can the negatives outweigh the positives? I think, as our former president Peter Dearman would say, no, they don't. So, yes, on behalf of the Ashford section, I'd like to say thank you very much. And obviously everyone else for attending. And John, you'll be.
Have we Colin?
I think we lost him. If he comes back.